My name is Chirag Patel. I'm an associate professor of biomedical informatics. As I give you a brief discussion of the definitions of the genome and exposome and how they're being correlated in large data, let me give you a couple of how-to objectives that I hope to accomplish today. So first, what we need to do is figure out the ruler. So how to compute the aggregate contribution of the genome, shared exposome, and the specific exposome and the phenotype to allow us to answer questions such as, what is the shared and specific exposome? How big is the exposome and how big is the genome in phenotypic variation? And secondly, how to apply new data science techniques to identify specific exposures that explain this variation that you measure in one. So for example, what are the actual specific exposome factors that drive the variation in phenotype? And how large are they? And what is the implication of these association sizes between exposures and phenotypes? So briefly, these objectives can be summarized into the first, which is defining this ruler and figuring out the parts of the ruler, the variation that make up this phenotypic variation. So you can imagine phenotypic variation being something you like to measure as a function of aggregate environment and genotypes. And the second is what exactly contributing to that variation? What specific factors are contributing? So first, I'll start with the ruler. So earlier we talked about definitions of the genome, the definition of this exposome. So how can we aggregate this computation to figure out how much variance that we have to explain for each of those different phenomena? So first is heritability. So this is the notion of the amount of genetic variation in the population. And so it's essentially the variation of genetics divided over the variation of total phenotypic variation. And the shared environment or the shared exposome is what we call the C-squared, okay? So that's the amount of variation that we can attribute to living in the same household, but not sharing the same genetics and the similar ratios computed. So how do we solve this in large biomedical data? So first, the way that we did it in the first case study to solve the aggregate contribution of each of these phenomenon is leverage a large healthcare insurance claims data set. So here we had millions upon millions of individuals, almost 45 million. And we were able to assess phenotypes by billing codes, procedures, drugs, and labs. And what we then did was merge that via zip code to variation in weather, air pollution, and socioeconomic status, all on an area level, to ask the question, what is the role of these specific shared factors with respect to phenotypic variation? But as you know, phenotypes, genotypes, and exposures are correlated and shared. So here's an example of a phenotype that we all know and care about, such as diabetes prevalence in 2016. And you can see how the exposures, or I'm sorry, the phenotypes are clustering in different geographies, specific geographies in the South and in certain places in the Southwest. This is also juxtaposed against the genetic contributions or phenotypic manifestations, such as the genetics that make up ancestry, like ethnicity. So a genetic component of that, but also a phenotypic component. Also a shared environment, such as income, and you can see how that's also clustering in these areas, or a lower income, as well as air pollution. So the idea is, can you disentangle all these contributing and sometimes competing factors to understand their joint contribution? One way you could do it is using family-based studies, and that's what we did in our first case study, is you can get an aggregate indicator of genetics by using families such as twins and siblings. So out of 45 million data points or individuals in this data set, we were able to get 60,000 twins almost and 700,000 siblings. And that's the primary advantage of using these administrative types of big data approaches, is you have a large sample size by which to do your data mining. And we had and so under the assumptions that identical twins share 100% of their genome, the fraternal twins and siblings share about 50% of the genome, you can use this natural experiment to slice and dice genetics and environment. All right, so how do you do it? You do it by using the difference between the rates that you observe in monozygotic versus dizygotic twins. And you can compute heritability as Falconer showed in early days of genetics. So essentially, you can partition the variance of genetics and environment by simply looking at the difference of correlation between diseases that you observe in monozygotic versus dizygotic twins, or identical versus fraternal twins, as we like to call them. And then with phenotypes out of the box in these healthcare data sets, you get many phenotypes measured all simultaneously, such as through billing codes. So here's examples of ways of measuring different diseases and phenotypes in these administrative data, in these different groups, for example. So here's the first sort of data point I'd like to share in this large data analysis is looking at 2 case studies of Lyme disease and obesity, which you can kind of intuit some of the contributions to each of these factors. So for example, for Lyme disease, you have a heritability estimate that is pretty much not different than 0. You have a moderate shared environment. And when try to partition the shared environment, you get a good fraction that is explained by seasonality. So things that you might intuit when thinking about Lyme disease and its clinical manifestations. With obesity, you have a significant total genetic component. You have also a significant total shared environmental component. And of that shared environment, you have exposome, you have a significant socio deprivation index, as well as that contribute to that shared environment. So how nuanced is this? So let's look at different phenotype groups. You can see that the variation in these estimates of heritability that I'm showing in this plot here is quite varied across these different groups. So on the x-axis, I'm showing these phenotypes grouped in different phenotypic categories of function or of disease class. And you can see how these bars, essentially, you can eyeball them and how they vary in their heritability estimates, but also in their shared environmental estimates. And overall, we get a heritability of about 30% and the shared environment about 10%. So a lot of nuance there in these measurements. And so that leads us to the question, if you order all these diseases from the lowest to the highest heritability to the lowest, where's the rest of the variation? So here in the color blue, you see the total genetic contribution. In green, the total shared environment contribution through the shared families and households. There's this mass amount of variation that we cannot explain in these complex diseases. So where do we go next? And so in summary, for that first case study, we get a very nuanced view of genetics and environment, or the exposome, in these broad collection of phenotypes as measured in the clinical record. So 58 had a non-zero heritability, 58%. 32% had a non-zero shared environment, but they were very modest in their contribution. So both genetics and environment play a role, a shared environment play a role, but it's a very small one, okay? And of course, age and sex had a strong influence as well. And shared environment does not actually equal pollution, income, and climate. It's a lot more than that, as we cannot untangle the shared environment completely in some of those case studies that I just showed you. So if you do the back of the envelope calculation, you have 0.32 plus 0.09, so the shared and the environment plus the heritability components, you get an estimate of 0.41 on average that you're able to explain in these large data sets. So where is the rest of the variation in phenotype is the question that we need to answer.